sure there's some.
Story short.
I was glad to do was one of them. They wouldn't notice. The one we had to do the circuit. Like that. The renewally one and home with one. Yeah, like when I actually calculated out what mine did. I thought I did it right. I did some research, but what are the right numbers? So I said, like, this equals that.
Yeah.
Don't be actually doing that.
Yeah.
So, maybe you found that.
That would be impressive. Because then it was hard to shot, right?
That's what I figured. It's like, he's not going to do 2 choose 4 times next time. He's going to do all the math.
But maybe
This one time. So,
It was really fun.
I can bring it to you tomorrow.
Like I was talking to another guy and I was
you
like,
guys
oh,
have weekends?
but wait,
did I have your computer to this?
That's week. It's week.
yeah.
We get right now. So. Do you have a lot of tests this week?
I got one this week.
We have like.
Are you graduating?
What's the reason?
He doesn't have to do ACC.
Oh, yeah, we don't have to do any sort of senior.
But now,
We have a software class,
Makes
but
us happy.
it's
32
a pretty
kids.
minor project, and everyone does the same thing, so, yeah. I think we get out easy on that. Do you choose what you do? Is it totally? You like remember it? Okay, that's good, because if you have to say the choice. What do you guys do?
it's like a wireless sensor. And all the sensors out for pressure, temperature, and then it's
In your computer thing,
yeah.
do you guys actually ever like do anything physically in circuits, or is it all like design? So you actually like wire it?
Yeah.
Oh, okay, cool. I figured it was all this like some simulation.
Yep.
That's so cool.
Our last year was more ultrasonic.
Yeah, we're on the same team.
Electrical engineering, like I had a never freshman year.
Yeah.
I was only on but you can the hardware. You can design it.
Yeah.
Software is so much more
Right.
I guess there's more need for software because it's
Right.
everyone needs that.
And
It's more concentrated.
You look at it and be like, nah, I can't take this. Even though it's happened so many times. Now I got the you can't for it in the first place.
No problem.
Yeah, you can't replicate left-hand intelligence. But I can replicate whatever. Yeah, that's a good point. Yeah. It's interesting.
No barriers.
That's a good point. That's why it's so popular. Just like make your own thing. So really, you should just break and build like a. Yeah, you're working tonight.
Yeah, but
For grad school,
That's great.
I know I was waiting. Oh, there's like oh, do this, then this, then this. You're good. The others just like, nah, you on your own.
well, of course, there's
No, timer. What else? I mean, probably input capture. Be different. Well, you know, SPI. I'll make it register as I go in.
yeah, that's fine.
Oh, God.
post this one on the grid. Hey mom and dad, this is my firmest achievements.
Your computer.
Not me.
Sure you guys do the same.
No, he's in honors.
Oh, okay. It's a special trail.
You have to do the final.
Oh, you got multiple people.
Right.
Anything goes wrong. That's tough. You just have to take, like, do they have sun
Or the solid grade.
Okay. So a couple of announcements, which I also have to provide by email. For the second time this semester, I have to cancel this Friday's lecture, but don't feel shortchanged. I owe you guys at this point 2 lectures with the one I'm canceling on Friday. And Unite is a great service. They allow me to record makeup lectures. And so I'll actually do the first one of those within the next 2 weeks, and then the second one a bit later in the semester. But the idea is I'll just pick a time that works for me and works for the Unite operators. It won't be during class time. It might be during class time on a Monday, because perhaps there's a chance that many of you don't have conflicts then. But if you can't make that lecture, the videos will be posted. So, okay. And the other announcement is that I'll have to end the lecture a little bit early today, which is uncharacteristic for me. Okay, and attendance is down from last time. Perhaps yes, Jordan.
About our makeup lectures, will they be posted immediately? Or
Yes.
Okay.
Yes, so I'm allowed to post those immediately without the 10-day delay. Yeah. I don't think it'll be a problem for this course because there are many disconnected topics, and I will discuss during those lectures a topic not directly connected to these. So, okay. Okay. So, yes, Ryan.
I just wanted to remind you, do you still want to go over those 2 things from homework 2, like show us the final circuit? I don't know if we have time.
Yeah, we do. Sure. I wonder if I can remember them off the top of my head. I can certainly remember one of them off the top of my head. So Ryan's request was there were 2, depending upon your temperament, either fun and intriguing problems on homework 2 or supremely vexing problems on homework 2. The first one was how to construct X and Y. So the problem here was using switches that are either open or closed, controlled by the variables X and Y, arrange them such that you can probe the resulting circuit in different places and get all 15 functions of 2 variables from the one circuit. And there's a solution that has 8 switches. So I remember the topology, but someone may have to help me actually arrange the switches, and we shouldn't waste too much time on this. So if we have X and Y and X. Yeah, this will be X naught, and this will be Y naught. But then, can someone remind me what?
So X naught is on the top. On
E-
the side.
Here, X and X naught?
X naught on the top left, and X naught on the top right.
Here?
Yeah.
And here?
And then X for both of them.
Here, X and X?
No, that's what X and X.
Oh, okay. I thought I heard a no. Okay. So I tried to prep you guys a little bit in the sense that the center part, you'll recognize, for those of you who got it, is the circuit that allows you to compute the exclusive OR functions. So these two functions, if we probe it here and here, then we get x, y naught, x naught, y as the possible connection between here. And between here and here, we have x and y and x naught, y naught. So the center box is kind of the hard part, to get these two functions with 4 switches. Then I also tried to prep you guys. In one of the earlier parts, I asked you to compute functions of the form a, b, or c. These are functions that I've actually spent a lot of time playing around with in a different context. But these types of functions you can get with a triangle. Now, of course, here we have 2 variables instead of 3, but the triangle configuration here allows you to get terms that, when you multiply them out, simplify to what you need. Anyways, what I'll do is I'll email you guys just the solution to this so you can stare at it and play with it. I hope this doesn't irritate those of you who didn't get this and played around with it for a long time. And yes, Jack?
I got a different circuit that also works.
I'd be intrigued to see it, because as far as I know that the solution is unique, up until like, I mean, you can take this, imagine this was a circuit, and you can twist it in various ways. You may even be able to take the nodes and, well, so is your circuit planar? Do any of the switches cross?
No.
No? And are you sure it's different from this one?
No, I can check that, though.
Because I don't know for a fact that this is the only solution up until permutations and so forth shifts, but I think so.
Okay.
Yeah.
I think the x and x not on the sides they should be.
Yeah, that makes sense. No?
No, because then you can say from, if you have E and F on the left, so E on the left side or F on the right side, then you have a short circuit between them. Because you have X on top and X not on bottom. So that'll just be 1. So essentially that becomes the same node. And then you only have 5 nodes and you're unable to produce 16.
Yeah.
Okay. I really want to get going, but let me just show you guys. And for this one, for those of you, now this will be the problem where you're asked to multiply 2 fractional values with chemical reactions. So you're asked to compute with a chemical reaction network the function C1 over C1 plus C2 is equal to A1 over A1 plus A2 times B1 over B1 plus B2. Now, many of you, I think, computed this by multiplying out this expression. It's not so hard. But then you've got a big expression with a bunch of adds and multiplies, and then you have to somehow perform the division. And this can be done with chemical reactions using the tricks that we've seen, multiplication that's iterative and so forth, and sticking this together into a program. But the motivation here is a collection of recent ideas with a PhD student of mine for computing things in a very different way. Recall that when we talked about stochastic bit streams, we talked about computing with probabilities. So in the case of an AND gate, if we had probability A, probability B of getting a 1 on the 2 inputs respectively, then we would have the output being the product of the 2 probabilities if they were independent. So perhaps you can begin to see the connection now that this fractional representation also gives you a number between 0 and 1. It's not a probability, but here what we want is we want the output fraction of C1 to be the product of the input fractions of A1 and B1. And so what we want is the output to be the right fraction in terms of the input fractions. And chemical reactions are inherently random, if you think about it. And so you get the randomness for free. And so you can achieve this fractional form of multiplication in a very, very simple way. And of course, I'll be very eager to see if any of you figured this out. So here is a set of 4 chemical reactions. The rates don't matter, or the rates can all be slow, so you don't have to worry with fast or slow iteration. And so the solution is simply A1 plus B1 goes to C1. And then all the other combinations, A1 plus B2 goes to C2. A2 plus B1 goes to C2. And A2 plus B2 goes to C2. So you have 3 of the reactions that go to C2, and 1 of the reactions that go to C1. And so this is kind of like the 1-1 case, the 0-1 case, the 1-0 case, and the 0-0 case. All 3 of these cases for an AND gate go to 0. They go to the C2 part, and only the 1-1 case goes to the C1 case. I'll talk about this reaction, this set of reactions a bit later in the course and why they achieve multiplication. What's interesting, for those of you who get interested by such topics, is here we've generalized the concept of multiplication in the form of, let's say, an AND operation on fractional values. We can also generalize the concept of, remember the business with Bernstein polynomials and Bernstein polynomials implementing arbitrary functions on chemical reactions? We can do all of that. So Bernstein polynomials implementing arbitrary power form polynomials in terms of stochastic logic. I'll show you how to do arbitrary polynomials through the Bernstein polynomial representation with chemical reactions. What's interesting about that is how simple and efficient it is. We can get by with, here multiplication was just 4 reactions. We can get by with, we can do a complicated polynomial with just 12 chemical reactions. And furthermore, all the reactions, the rates can all be slow. We don't need any fast or slow reactions. It seems like a really good way to compute. This is all very new stuff. We just submitted a paper on the topic. Did anyone come up with this? I guess we'll see.
I had a similar thing. I was using different equations for multiplication, but I mean, I had these 4 constituent equations.
Yeah, very good. I wasn't, so here I can fully appreciate, it's, I think, a very common, perhaps universal intellectual failing. We have complicated brains, complicated thoughts, and in order to understand the world around us, we look at these other entities that we're interacting with, people, and they're complicated to understand. So a good first-order attempt to understand how other people behave is to take our thought processes and imagine that the other people have the same thought processes. This is very useful. If someone appears angry, you think, how do I feel when I'm angry? And then you say, okay, this is how they must feel. But when we retreat into the intellectual world, it's very easy to assume that other people are thinking what we're thinking, and other people know what we know. And this, I think, is at the heart of the problem of why technical presentations are so bad. If you, graduate students here, you go to the seminar series, some of the seminar talks are good, but a lot of them you have this great expert on nanomagnetics or whatever the topic is coming to talk about his work. He stands up in front of the crowd and gives a presentation that is so abstruse that nobody in the audience can really follow what he's saying. The guy's not an idiot. And he knows that the audience doesn't know that the audience isn't an expert, but still he can't give that talk. Why? Because we can't take ourselves outside of our head to understand that other people don't know what we know. And so, all of that to say, for this problem, I knew this solution. And I wasn't expecting people to come up with that solution, but I gave the problem anyways. So that said, you'll receive full credit if you had a complicated scheme with iterative decrements to do multiplication and so forth that worked. But as with all these topics, I'm interested in your input. Okay, any further questions? Okay. So, jumping right back into the pond here. This topic, as maybe you can tell, I get excited about whenever I teach this topic on conditional permutations. But somehow, even though I've taught this a few times, and I get excited about it each time, I haven't really succeeded in following up on it. So if any of you are interested in pursuing this topic as a research topic, of course I welcome that for all topics, but this one in particular, I'd be really eager to talk to people about. Here is, again, to set up the basic premise. The basic premise is we have a circuit that computes a function. In a sense, I'm presenting everything backwards because I haven't shown you guys a circuit to compute the majority function. So suppose that x is the collection of variables x1 through x1024. So we've got 1,000 variables, and we want to compute the majority. We want to compute a function that's 1 if at least half of these are 1. I haven't shown you guys the circuit for it, but I will after presenting conditional permutations. So there's a circuit that computes the majority function. But in general, we may have a circuit. And what we're talking about here will be, there's two ways to approach this. It can either be a data structure. Data structure. So a data structure, and in fact, it is binary decision diagram. So it'll either, we can view this as a data structure, like a binary decision diagram, so a graphical way to represent the function. I tried to explain, I don't think I gave a good justification, why data structures for Boolean functions are interesting and useful, but they are. They're at the heart of the entire discipline of electronic design automation, or CAD for circuits. We need a way to represent the function that the circuit computes. We need a way to represent it so we can do things like check if two circuits compute the same function. Or more broadly, when we want to synthesize a circuit, we're going to synthesize a circuit by synthesizing portions of it and then combining them together. So to figure out how to combine them together in our computer program, we have to have a representation for the functions they compute. So binary decision diagrams as a graphical way to represent Boolean functions in general, as I introduced it, have been very useful. This is a very specific and, in fact, I don't think anybody other than me has really considered conditional permutation programs as a binary decision diagram or even as a data structure. It's kind of a novel way to package it, but it is just a binary decision diagram. And I think there's interesting research to be done to just explore the data structure in various ways. So, John, I think last time, was it you or was it Jason? You made the observation, or I think it was Jacob. So what are some essential features of a data structure for a Boolean function? Like, I mean, why not just use the circuit as our data structure? If we... I think you did. Or maybe it was Mackenzie. So you had... tell us again your comment.
I don't remember what I said. Wasn't it because the circuit doesn't change when the inputs change?
Right.
In the BDD, we can see other things with those changing inputs?
Yeah, exactly. And if we want a task like determining if two circuits compute the same function, an essential property of the data structure, it was Jacob, you said that the data structures, if the representation is unique, then sorry. That was Scott. All right. So this is what Scott said, that if the data structure is unique, then you can test whether two circuits compute the same function for free if you can get the representation, in essence. Because if there's only one way to represent a given function, once you have the representation for the circuit, you can just check if it's the same for both. So the circuits are different, but if the underlying function they compute is the same, you can test this if your data structure has that property, that there's only one way to represent a function. Conventional binary decision diagrams have that property. I tried to prove it. That was the very muddled lecture where I was trying to prove that there's only one way to represent a function. But as it turns out with these conditional permutation data structures, they are binary decision diagrams, but they don't have that property. So can anyone say why? This is jumping into the topic, but why don't they have that property? What's different? It's a binary decision diagram. Okay, let me go to.
Because you can always put in A and A inverse anywhere, and it will just. You can put in A and A inverse.
Put in A and A inverse, yeah.
As in, you can one permutation, and you can put a reverse of it in some later stage.
Uh-huh.
It will kind of cancel out. It will make identity.
Yeah, that's. I'm not sure. There's a simple. Basically, when I was presenting this, even on this slide, there should be something about this binary decision diagram that strikes you as different from the other binary decision diagrams we talked about. What's different here? Recall the other binary decision diagrams, we first started with the complete binary tree. We merged the 0 and 1 buckets. Then we started merging the nodes, merging the nodes, merging the nodes. And I argued that the final result is always unique. Here, the way that I started writing it down was messed up to begin with. So what's wrong with this, Jason?
Well, they go straight down instead of branching in.
There's nothing wrong with that. But even here, so what? X1, X2, X3, oh, shoot. So this slide doesn't show it, but I thought one of my slides does. Oh, maybe not. Okay, I understand now why you're not. This one does. So here, notice that X1 is repeated. So in a conventional binary decision diagram, you have your variables. You have them ordered. Let's say you have them ordered from 1 to 1024. The ordering is something that people play around with, but the idea is that you fix the ordering. And the whole argument that a binary decision diagram is unique, there's only one way to represent the function. It's unique up to the variable ordering. If you change the variable ordering, you get a different decision diagram. So here, as you'll see, the conditional permutation programs that we come up with, not only do we not specify the variable ordering up front, so if we have two circuits, in essence, we don't have the luxury of specifying the variable ordering. The variable ordering will be decided once we begin constructing the decision diagram for it. But also the variables will be repeated many times. So it's just a different beast, and this beast does not have the property that it's unique. So, again, paraphrasing what John said a couple of lectures ago, why is this interesting? You're teaching us a representation for a circuit that may be narrow but very long. And now I'm telling you that it's a data structure, but it doesn't have one of the essential features of the data structure. That's true. But I think that perhaps we can make it unique. Or at least we can begin to approach the uniqueness property of it. And this will have to do with, once we have it in a conditional permutation form, how we can just begin to shuffle the permutations around. But the other idea that always gets me excited whenever I teach this topic is, as I mentioned briefly, it can be a pipelined circuit. So this is what I attempted to draw here. A typical structure for a circuit, a logic circuit, will be one in which it's really in a quasi-tree form. So we have the function that pops out at the bottom. To compute it, the tree grows upwards. In general, it won't be a proper tree. So this tree is not a proper tree. Why, Jesse? Yeah, so if you think a proper tree, branches never grow together as you go up. So there is reconvergence or merging as you go up. But still, so this is in a lattice form. It's directed, or we can have a partial ordering among the nodes in the tree. But at a given level, because of merging, it won't be a proper tree. But the circuits are nearly tree-like in the sense that they grow up, but they get wider and wider. And the more merging that we can do, the better our circuit. And so, in a sense, the whole field of logic synthesis is how to do as much merging in the computation as possible, because the more merging that we can do, the more logic that we can share in it. Now, a given circuit like this, to compute a function like majority, has the feature that the depth of the circuit, so let's talk about the depth. Will be important here. If we had a complete binary tree, so if we had a node that split and split and split and split, then if we have n variables, what would be the depth of the circuit? So the depth, if we had a complete binary tree, depth, so n variables, depth would be, and here, this is actually not an unrealistic assumption. We'll just assume that every gate is a fan-in-2 gate, so 2 inputs. And without loss of generality, we'll just assume that they're all AND gates, and there are bubbles in places. So we can have some NAND operations. But just imagine these are all 2-input AND gates with bubbles on some of the outputs, giving us NAND gates. That's actually a typical form for the circuit. So with n variables, the depth will be, for a circuit that would be a complete binary tree, would be log base 2 of n. Because a complete binary tree, we're aggregating variables at each level, 2 by 2 by 2, and so we can get from n variables down to a single output node in a depth log base 2 of it. For real circuits, because of this sharing, this reconvergence, the depth won't be quite log n, but it'll be much closer to log n than it will be to n. So if we had n variables, if we just stacked up, if we had, with the screen down, I'm running out of space here. So here it would be a terrible circuit. A circuit that had this type of form, where it's essentially linear. So here if we had x1, x2, x3, all the way down here, x10, 24, the circuit would be would have depth that was equal to the number of variables, or linear in the number of variables. So here the depth would be n. So real circuits are much closer to log base 2 of n depth than to n depth, but they're somewhere in between. And so here, with the conditional permutation programs, it's a way to transform a circuit that has a tree-like structure, or a structure that's close to log base 2 of n, to a circuit that has linear, it's actually worse than linear depth, that has quadratic depth, log base squared of n. So again, why am I showing you guys this? Because a circuit that has such long depth will be one that has very long delay. Or as John said last time, you've got all these instruction cards. So what's the point? Well, the point is that the circuit, even though it has relatively long depth, the depth is not exponential in n. So if we have 1024 variables, we'll have about a depth of 1,000,000. So it doesn't grow that badly. But also with the conditional permutation programs, the structure is extremely regular. I just want to get through the full example. Sorry about this. I hate it when someone does it, but whenever I go out of presentation mode, then the screen disappears because of the stupid mirroring of the display. Okay, so here is the conditional permutation program that computes that function. It's just a pipe. So the exercise here is to take the circuit which is in tree-like form. Imagine now that it's plasticine, and we squeeze it into a pipe, into a long pipe. But it's a pipe that has an extremely regular structure, meaning that it's just, at each step of the pipe, we compute one permutation or another permutation depending upon the value of the variable. So imagine now that we actually would build this circuit. So if we would actually build this circuit, here at each level we would have to access a variable. So x2, x1, x768, x3, x4, x777, and so forth. And here, what would we do? Well, the permutation part of it, we can translate into a very simple circuit. Basically a simple circuit with perhaps as little as 10 transistors per level, 10 transistors. And so now, suppose that we were to exploit this idea to build a heavily pipelined circuit. So Alex, you took the course on architecture. Remind us again, what is a pipeline circuit or pipelined architecture?
Pipeline architecture is when you can, it takes a certain amount of time to do an instruction because there are a lot of little steps along the path.
Mm-hmm.
In the pipeline structure, you put one instruction in the first step, and then after it moves on to the second step, you put in another instruction, and you just keep putting in instructions as they go through the steps so that you can execute your function roughly as many times faster as you have steps in the pipeline.
Yeah, very good. So in computer architecture, this was a revolutionary concept when perhaps 30 years ago people started moving towards RISC, reduced instruction set architectures, and then pipelining. It made our computers a lot faster. At the level of instructions, this is kind of at a higher level. At a circuit level, what would pipelining be? Well, the concept would be the same in the sense that a computer does things over and over and over again. So if you just wanted to evaluate a function once, then this would be a poor choice because you would have to wait the full length of the pipe for your answer to come out. But with a computer, you're computing something, but there's always something that you're computing next. And so even though for your circuit to start up and produce its first value will take a long time, if we can keep the pipe full of computation, that won't matter, because after the first value pops out, the next value will pop out immediately and immediately and immediately. The analogy, I think you guys all get this. And I think from a physics perspective, this is very interesting. I'm designing an irrigation system for my property, and so looking at calculations for water pressure and pumping. And it's really true that if you have a long pipe, the hill is everything. So pumping water up against gravity takes energy. But if you have a pipe that's just running horizontally, even if it's running for a great distance, it takes no energy, almost no energy, literally, to move water through it. Why? Because it's full of water, and when your pipe is full of water, then you guys get this. Then it takes very little pressure to push molecules out at one side relative to pushing them in. So that's exactly the same concept here. So where am I going with this? Imagine that we would set up, and this could be a programmable architecture. So we would program the circuit that does the permutation part at each level would be programmable. So we could change it to get a different function. This would be easy because there aren't many permutations we have to consider. It would actually be 12 different permutations. So a circuit that we could say, at this level, do a particular permutation, do C. If the variable is 1, do D if the variable is 0. So easy to set up this programmable substrate. We would also need a routing architecture, and this will be the hard part, that can route variables to arbitrary, let's call these rungs in a ladder. So I'm mixing metaphors. This will now be a ladder. So for each rung in the ladder, we need a routing architecture that can say, now I want X777 at this particular place. But imagine if we've got that set up. Then we can have a circuit that computes a combinational function, a function of these variables, based upon the values of zeros and ones that we assign to the variables and the permutation it computes. Then for the next the next time we use the circuit, because we use the circuit over and over again, the values of the variables will change. Their positions won't change, but the values of the variables will change. And so we would have the current values of the variables that would be stacked up here, and then the new values that would be, in essence, following immediately as we walk down the ladder, just one rung behind. This would be the next set of values. So the computation then would be entirely stacked. And here we could do this perhaps with some kind of clocking mechanism to synchronize moving down the ladder. Or, because everything is so regular, we could just build the circuit and count on there being relatively small timing variations in the time that it takes our circuit to execute, and simply have no clock, just have values going through, chasing each other, and chasing each other very fast. This could be exciting. I'd really like to explore this idea. Okay. Any questions on this? If there aren't, I'll return to the conceptual part of explaining how we can compute with permutations, because I still haven't. But John, any questions on this? Ask him.
No, it just became clear.
Okay. It's not clear to me, so I'm glad it's clear to you. Yeah.
The reasoning here.
The reasoning. It's still not clear to me. So here's the challenge. So I'm going to be honest here. Every time I think about this, I kind of go both ways. Is it a good idea or a bad idea? Here's a reason why this would be a bad idea. So suppose that this idea of the conditional permutation programs it's one way to complicate the whole issue. But suppose there was an obvious way to take a circuit like this and transform it from a tree into a ladder. Suppose there was an obvious way to do this without the conditional permutations. Then people would have thought of this idea before. I don't know of an obvious way to do it. But so what I'm asking for here is imagine that you have an arbitrary circuit, a lattice structured circuit like this. Each gate is a fan-in-2 AND or NAND gate, and that's your circuit. That's a typical representation. Can you take that circuit and squeeze it into the form of a ladder? And consider the circuit to do majority. So before, when I said, you could have a circuit that's linear in the number of variables, there's no way that I know of, an obvious way, to flatten this circuit that computes the majority of all these variables, x2, x3, ... all the way to x 1024. And so you might repeat the variables. But if it's linear like this, how do you count whether you have over half your variables equal to 1? If your ladder is relatively narrow in width, you can't communicate across rungs of the ladder a count value that you're preserving. Whether you have 256 ones that you've encountered so far, whether you have 400 ones that you've encountered so far, and so forth all the way down. So I don't know of any way to do this, but there might be a way to do this. Then again, when I go back and forth on this, probably not, because the PhD thesis off of this which is based, it was a big result at the time that the guy, he was interested in theoretical computer science, not circuits, but it was a big result that he was able to show that you could compute majority and he actually considered arbitrary functions, but the majority function was the target function, that you could compute majority with limited memory. And so if it was obvious to take a circuit, and people know of the circuit to compute majority, and transform it into a ladder in some obvious way, then the people would have thought of that and they wouldn't have been impressed by his work. So I go back and forth on it. But, so any immediate thoughts on this, Jacob?
So if you're going to reprogram it, then you kind of have to have each of the x's available for each rung
Yeah.
of the ladder.
Oh, yeah. So, okay.
So it kind of means that you have to route them all
Yeah.
down the side. So
Yeah.
it kind of increases the width of the circuit.
Absolutely. So for a circuit implementation here, there would be some sort of backplane. The backplane would have all your variables racing in a track down. And of course, it would increase the width. But the programmable part would be simply that you can tap any variable that you want on any given rung. But again, it's true that the width of the circuit here would be, the entire circuit to an approximation would be that backplane, routing your variables. But you have to route your variables in a regular circuit anyways. Like, I mean, if you have 10,024 variables, it's not as though you don't have to route those to a lot of different places in your circuit. Yeah, John?
I mean, getting into the realm of architecture,
Yeah.
if you have like a jump and link or decisions to make, you'd have to wait for that pipe to get completely filled.
Well, but this would be in a different context. It would be at the circuit level. So at the circuit level, because this will be if the idea has legs, this will be a plug-in replacement so now for the non-computer engineers in the class, this is what we teach in our Introduction to Logic Design course. We build a computer, a simple computer, or a finite state machine, by taking combinational logic. So this would be a circuit that just consists of logic gates that computes a function. The inputs might be the variables, x1 through x1024. And then this goes to a register. The register consists of memory, so whatever the outputs of the computation are. And then those values are fed back. So on a rising edge of a clock, the next state becomes the current state plus the input determines the next state. And our machine is alive this way, so the clock pulses. This would be a plug-in, this would be a replacement for the combinational part here. So for the combinational circuit, we would stick it in here. And the idea here is that you want to reuse your combinational circuit. So you reuse it in the sense that you've got new inputs, and you compute a new output. Then you have new inputs, you compute a new output. So suppose we could replace this with a pipe. That pipe then would always be computing a new output as a function of the new inputs, and the new inputs would be pipelined very tightly through this pipe. Does that make sense, John? But comments, I'm interested.
My understanding was that on every clock pulse, right, the entire circuit also included the permutation would change, such that an instruction was coming down the pipe.
Well, actually, no. So the order of the permutations will be fixed. So this will be the program. What I meant by programmable, this is to say that the entire circuit, like an FPGA, could be one that we build, and then we program it for a specific function. We won't be reprogramming the function that computes on the fly. We'll do that once. Does it make sense?
Yeah.
But we will have to change the values of the variables, because that's what we have to change.
I was just understanding it as like this was a single, this would replace the ALU with a single pipe where you could run any instruction down it.
No. I know. That's interesting.
Okay, I guess
It's actually a fascinating topic. Circuits that reprogram themselves. So this is a different discussion. But like an FPGA is a circuit that you can program. So you can electrically program it to compute a different logic function. You can easily have an FPGA compute something, and based upon the results of the computation, reprogram itself. And many years ago, people got very intrigued by this idea, and some people thought it would revolutionize computation. And it's just very hard. I don't think it's widely done in practice. It's just really hard to even begin to design circuits that way. So that's a whole different topic. But what I'm thinking about here is much more conventional, that we just have a pipe, keep the pipe full. The question is, and this was exactly Jacob's comment, the backplane that has to route the variables all the way through, how expensive is that? Maybe not that expensive. Like, this circuit has 1024 variables. You have to route 1024 variables, to certain places in the circuit. Just have parallel lines, tap those lines with some sort of regular multiplexing architecture for the programmable part to decide what variables go where. The drawback might be, so if you think of it, so forget about the programmable part, just comparing it to conventional implementation. In a conventional implementation, a given variable x1 may appear in just a handful of places near the leaves of the tree. Here, you may need that variable x1 in many more places, but not that many more. It's that perhaps won't be a very expensive cost to pay to get a circuit that produces an output basically the delay of the circuit will be the delay of one rung of the ladder here. Just one rung of the ladder. Imagine how quickly the circuit can compute. It means that in terms of your computation, you could pump this up not to 3 gigahertz, but to 300 gigahertz, because it'll be just the delay of one pipe. I'm fantasizing here. I do this a lot. Okay. Let me return to the topic of actually showing you guys how to compute with these conditional permutations, because I didn't explain it properly. I just basically got started in the computation. But that said, based upon what I've presented, can someone begin to explain how we can take a circuit like this and translate it to the conditional permutations? Can someone remind us? How about some new victims? It's Jared, right?
Yeah.
Yeah, okay. Can you remind us? Were you here last time?
I was, but I don't have my notes to reference.
Yeah.
Can't come up with it off the top of my head yet.
Okay. So I don't know where to jump into the explanation. Okay, let's start by listing what we've got, because once you list it, then it demystifies the process. I won't explain what I mean by a permutation, just to say that it's a shuffling. When I put it in parentheses, this is the shuffling E here is take the object that's in the first position, put it in the fourth position, the object that's in the fourth position, put it in the second, the object that's in the second in the third, third in the fifth, fifth in the first. So it's cyclic. So it's just a way of specifying how we can shuffle 5 objects. I've given names to 10 of these permutations, A through E and A inverse through E inverse. The inverse permutations are what they suggest. So if in the permutation E, I take 1 and I put it in the fourth position, in E inverse, I take 4 and I put it in the first position. So the inverses are just reading these backwards. And reading these backwards is just if I shuffle it and then I reverse the shuffling, I get back to what I started. So if I do the E permutation followed by the E inverse permutation, I haven't shuffled things at all. And so now, the critical feature of this particular set of permutations, and it's not unique, by the way, as I said last time, so the choice of A through E isn't unique. But what we can prove is that there's no way to accomplish what I'm about to tell you this accomplishes with permutations that have length only 4. So if you only have 4 objects, this doesn't work. If you have 5, 6, or 7, it does work. Any number greater than 5, greater than or equal to that, it works. What works? The following works. If I take any one of these 10 permutations, so let's say I take E, I can obtain the E permutation from the A and B permutation. So I can do the A and B shuffle. If I do the A and B shuffle and the A and B shuffle inverse shuffles in a specific order. So in this case, I do the B shuffle, then I do the A shuffle, then I do the B inverse shuffle, and then I do the A inverse shuffle. So that just corresponds to the E shuffle. And last time I went through an example what that would mean. Well, we would have the 5 objects, show that when we shuffle them, do the inverse shuffle, the overall effect is the same as one shuffle. Here, this operation is associative, so I can do the BA shuffle, and then do I can do the B inverse and A inverse shuffle, and then I can do the resulting shuffle. But it's not commutative. Obviously, AB, A inverse, B inverse is different from BA, B inverse, A inverse. Okay, but so to understand or accept this, I could present mathematics that proves that this set of 10 permutation exists. Or you can just sit down and do it, just verify. Or more concretely, for each of the 10 permutations here, figure out what set of other permutations gives you that permutation. That's the first observation for this set. So, Jared, how does this then correspond to an AND operation? Or anyone else? I babbled a lot, so I'm running out of time here.
Like putting a couple permutations together and getting another permutation out, or?
Well, as we'll see in a moment, things are conditional on a variable. the variable is Boolean. So the variable x is either 0 or 1. If we have two variables, x and y, we can talk about the AND function on x and y. So let me write that down. So if we have x and y, the four values we can have are 0, 0, 0, 1, 1, 0, 1, 1. So suppose that the 0 case will be the case where we perform no permutation. The 1 case will be where we perform, let's say, the C permutation and corresponding to x, and the B permutation corresponding to y. So in our program, if we have the program structured listed as this, we have the variable x, and then in the one case we do C, we have y, in the one case we do B, then x, we do C inverse, and then y, we do B inverse. These are the one cases for the variables. For the 0 cases, let's just put, what am I using for identity? I use star in this notation. So this corresponds to the 1 case, the 0 case for the program. So it means that based upon the value of the variable, I do one permutation or the other, 0 or 1. So in the 0, 0 case, I'm going to perform star, 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 star. I'm going to do nothing, do nothing, do nothing, do nothing, like my cat. So it means that the result is nothing. My cat is sleeping exactly where I left her this morning. She hasn't even moved a whisker. So that's one case. In the 0, 1 case, we're going to do nothing for x. Then we're going to do b for y. We're going to do nothing for x. Then we're going to do b inverse for y. So nothing followed by b followed by nothing followed by b inverse is the same as just b followed by b inverse, which is nothing. We haven't shuffled them at all. So you get the idea. Here we have now c, nothing, c inverse, nothing. So the result is nothing. Now finally, in the case 1, 1, what we're going to do is we're going to do c followed by b followed by c inverse followed by b inverse. So we're actually doing something. And if we look up there, cb, c inverse, b inverse gives me a. So this program, this seems really stupid. I'm just listing different ways of performing shuffles and observing that doing CB, C inverse, B inverse gives me some shuffle A. That in itself is not going to be useful. What's going to be useful is the fact that if I get A as my resulting permutation from these 4 steps, that permutation, I can use the results of that computation, that permutation, as part of a grander sequence of conditional shuffles, and that as part of a grander sequence of shuffles. And ultimately, I can take a circuit, which is the sort of circuit that I had listed before in tree form, and just translate it into a pipe of these conditional permutations. So are people seeing how? And actually, the way that I'll present it next is wrong. It's not wrong, there's no errors in my slides. But I am making a critical mistake. Let's see if anyone can spot it. Critical mistake that will perhaps negate the benefit. But I know how to fix this. It's okay. And the key here is that I'm starting from the bottom instead of from the top. Yeah, John?
I have a question
Yeah,
about these
please.
4 steps. I guess, to me, why wouldn't you do the first 2 steps? So x, and if it's 1, do c, and y for the second one, and if it's b, do 1, do b. And then multiply no matter what you have by c prime, d prime. And if you get a, then it's 1. Otherwise, it's 0. Does that mess up further computation?
Oh, no, but explain that again. I wasn't following. So, okay, this is interesting.
So if you do the first 2 steps,
Yeah.
and then put it through c prime, b prime, no matter what. If you get a, you know it's 1. Anything else, you know it's 0. Is there anything lost there for future computations?
Well, but you're saying, let's say the result is C and nothing.
He's saying replace the last two stars with the symbol next to it, like the bottom with the type prime.
Like that? Okay, let me think for a second.
No, that's, no, never mind.
I don't think that works, but
That's not what I was asking.
So,
I guess
but-
I'm not clear.
oh, please repeat it.
So if you do the first two steps.
Yeah.
And then you have a third step.
And the third step is just always do C prime, B prime.
Right.
Okay.
Is the only reason you don't do that because you want it, if it is 0, to be nothing and otherwise be A? Because I see it could be A, and if it's anything else, you know that it's 0.
But in this case, the result could be B, C prime, B prime.
Right.
It's supposed to be 0. Yeah, okay.
Okay, so that's.
No, but
that's the question. That is-
yeah, but that was a very good question. So it's by design here that the 0 case corresponds to the nothing shuffle or the identity shuffle, and the 1 case corresponds to a specific shuffle. And it'll be important that it always corresponds to the same shuffle. So, because we can, in other words, if the function evaluates to 1, if the AND function evaluates to 1, we always get A. We don't sometimes get A, sometimes get. Yeah. But was that? It was interesting what you were asking. I'm not.
Yes, the conclusion is that if it's 0, you want nothing.
Yeah.
I was thinking if it's 0, it's not A.
Oh, it's the opposite. It's anything other than A.
Yeah.
That would be different. The scheme that I'm going to propose won't work, but interesting. Think about all those ideas.
Okay, that's just,
Yeah.
I was just clarifying.
Okay. So here, and as I said, I have to redo these slides because maybe it's simple the way I explain it, but starting from the bottom is wrong. We should actually start from the top. We should start from the top of our circuit and build the circuit as we go down, instead of starting from the bottom and building our circuit up. What do I mean by starting from the top or the bottom? So imagine here that we had the circuit which I erased. And so, actually, it won't take much time at all. Can someone help me draw this? So it's going to be, if we start at the top, there's going to be an AND gate with X and Y, X and Z negated. And then there's going to be an AND gate here with X prime. I'll put, okay, I use primes there, so X prime, Y prime, and then I AND those two together. That's it, right? Okay, here's my resulting circuit. So the way that I'll present it, what we'll do is imagine that this entire circuit was covered with a piece of paper right down to here, and then we're gradually going to pull the paper up. That's one way to view it. But I think the proper way to explain this is we should start with the entire circuit covered and then gradually shift the paper down to reveal it. The difference is subtle, but you'll see that it makes a difference. But here is the explanation of how we build it. So what we do is we start by saying, without loss of generality, that the output at the bottom computes A. So we'll decide right at the beginning that our overall circuit will compute the permutation A if the function evaluates to 1. And so let's call it our function, f. If our function evaluates to 1, it should compute the permutation A. Otherwise, it should do nothing. So the overall result, once we're finished, is if the function evaluates to 1, we want it to shuffle things according to A. And if the function evaluates to 0, we want it to not have shuffled. This function is what we're going to expand as we build the circuit. So it's like we've packed the entire circuit into a single line here. But of course, we want each line to have a variable as the condition, not a function. But a function evaluates to 0 and 1. A variable evaluates to 0 and 1. So I think it's meaningful the way I've written it. So we start with the function computing A or nothing. Now we're just going to expand it. So what comes next, Jared? How do we expand it? What we're going to do is just expand the function, starting from the bottom. So we're going to say, all right, if we want the circuit to compute A, well, the only thing that I showed you how to do is to implement the AND operation. I think I also talked about negation. We'll have to remind ourselves how to do negation. But for now, we want to compute the AND function of A. So to compute the AND function of A, we want a circuit that now computes the C permutation and the B permutation. Why? Because we'll put those together into a conditional permutation that gives us the AND of these two. So recall that the AND permutation is going to be C, B, C inverse, B inverse, conditioned upon these two variables. So let's call these two variables alpha and beta. So alpha and beta will in fact be functions. We'll have to continue to expand those functions, just like here we have a function that we continue to expand. But suppose that alpha was our variable and beta was our variable. Then our full solution would just be this, C, B, C inverse, B inverse. If this was alpha and beta and alpha and beta. Of course, alpha and beta will be functions, so we'll continue the process. Is it making sense, Jared, so far? Yeah. Not? Ask. How can I clarify?
If those are alpha, beta, is that corresponding to like the zeros and ones of the x, y?
It's just corresponding, yes. So here it's as though for alpha, for x, I call this alpha, and for y, I call this beta. In fact, alpha will be the function xz prime. Xz prime. And beta will be, what's beta? It's going to be x prime, y prime, prime. X prime, y prime, prime. But a variable is either 0 or 1. A function is 0 and 1. I'm just substituting alpha for x. And so now this overall circuit should compute the AND of my alpha and beta, or the AND of the two expressions, which is what I want. So what comes next? Jared, what do I do next?
Move up again?
Yeah. So to move up again, what I do is here, any line that computes C, so this line that computes C, instead of having it compute C conditioned upon a function, I want to tease apart that function. So the function will get simpler and simpler. But I have to look up in my table which pair of permutations gives me the AND operation resulting in the C permutation. So that, I'll just go back to the table here. And I look up C. Oh, I look up C. For C, I need an E and a D, and an E inverse and a D inverse. So here, for the C, I'm going to replace the computation that gives me a C with 4 lines that give me, what was it again? I can't even remember for 10 seconds. D and E? ED. ED. So I'm going to replace that with ED, E inverse, D inverse. But I'm going to tease apart the AND operation. The twist here is that it's not an AND operation I want, it's a NAND operation. So what am I going to do, Ryan? How do I do the NOT operation?
Just reverse what you have.
Close. And that seems intuitive, but you can't actually just reverse it. But what we'll do is a trick that doesn't cost us anything. So, how to explain this? Suppose that it wasn't an AND operation. Then what I would have here would be just xz going to D inverse, DE inverse, D inverse E. That's what I would have. But since I want the NOT of that, so the overall set of permutations here, if I just erase the C and the C, DE, D inverse, E inverse actually gives me C inverse if I look it up in the table. It gives me C inverse. If I take the C inverse and I multiply it by C, I get identity. And here, I also multiply the other one by C. So this is, it's as though, that's what I showed you last time. It's as though there was an extra line in here that was just always multiply both by C. So I multiply this one by C, this one by C. That doesn't cost me anything. What I can do, in fact, is here just the permutation that I do in the case of Z will be E inverse times C. I'll do both in one step. It doesn't cost me more. It's still just a permutation and C. Is that making sense? Or am I losing people here? All right, so this means I've done the AND operation, and I've done the NOT operation at the end of the AND operation. I've replaced just that one line. I have to do it for all the lines. So now I have to do it for the B, the C inverse, the B inverse. But I just keep doing this. And when you first see this presented, you might say, all right, well, as you're starting on the bottom, as you're going up each level, or as you're continuing to expand the circuit, you're multiplying the number of instructions by 4. And that multiplying something by 4, this means it's exponential. An exponential, if you're a computer scientist, is like, it's like, so if you come up with an algorithm that's exponential, let's imagine you had a big inflatable balloon creature, and it's like it's slowly deflating. Your interest in something is disappearing when you begin to understand that something's exponential. Except it's not exponential here. Why not? Does anyone follow? So Mackenzie, why is it not? It is exponential. But it's an exponential that isn't as devastating as it seems. Pardon me?
Is it because it's
very good?
It's actually linear because it's 4 times the number of operations.
So it's going to be exponential. It's going to be, in fact, to the power 4, but it's going to be to the power 4 in the depth of the circuit. And the depth of the circuit is logarithmic in the number of inputs. So we're taking an exponential of a logarithm. That's not so bad. That's, in fact, linear, in this case, quadratic. I'll explain it to you. But taking an exponential of a logarithm is a lot better than just taking an exponential. In fact, it can be good. It can be linear. I'll explain. But first, let's just complete this example here. So what you can do is continue to expand each line. Why is this not working? OK. So next step. Computer's thinking. So here, all I'm doing is I'm continuing to expand everything to the final form. There's no trick or subtlety here. I'm simply expanding, expanding, expanding. Whenever there's a negation, so there's going to be a negation here and here, I do the trick that I actually compute the inverse of the one that I want and multiply the last line by the inverse to get the permutation that I want. So it doesn't cost me anything, but you'll notice that some of the lines now have a pair of permutations to get that negation as part of the condition. And also, I no longer have the structure that I had at the beginning, which was very nice, where I had simply permutations for the one case and identity for the 0 case. Because of this, now I have, in some cases, identity and permutation. In other cases, I have... and so why did this happen here, this last step? John?
Why did the last step happen?
Yeah, so why here do I have identity D? That's the opposite of what I usually have. I usually have permutation identity. It's X prime. So when you get to the final step where you have a variable, if you want the complement of the variable, then you can just switch them in that final step. OK. Right. But let me explain why the overall result is, in fact, it's in fact going to be quadratic in the number of variables. So is anybody seeing this? So, Mr. Ryan, why is it quadratic in the number of variables, the length? If I have 1,000 variables here, I'm going to have 1,000,000 lines, roughly. Why? This is just, I'm never very good at this, but this is going to be very simple. I think high school level calculations with logarithms and exponentials. So let's call this depth D. Now we're agreed, or we have to agree upon, the D is going to be roughly equal to log base 2 of n, where we have n variables. our conditional permutation program will have number of lines, equal to 4 to the power d. Because for every step that I go up in depth, every expansion that I do, I multiply everything by 4, by 4, by 4, by 4. So the number of lines is going to be 4 to the power d. Well, this is equal to 2 to the power 2d. Is that right? And so this is equal to 2 to the power 2 times log base 2 of n, which is equal to n squared. Everybody's okay with this? So you just take the 2, put it up here. You can do that with logarithms, so it's n squared. So if I have 1,000 variables up here, I'll have a circuit that has depth 10 in general, or roughly depth 10. And for a circuit that has depth 10, I'll have 1,000,000 lines. So for 10,024, I'll have 10,024 times 10,024. So that means that here the exponential part of it, the 4 to the d, which looks devastating, is not so bad because it's 4 to the power of a logarithm of the metric that's expanding with the number of variables. And n squared really is not that bad, a pipeline of length 1,000,000 for circuits in terms of the structure. So we can compute a complicated function, and a function of 1,000 variables is a complicated function, with only 1,000,000 steps in a pipeline that we can heavily buttress. Now, so think about this before next time. There's nothing wrong with what I've shown you. I think everything on these slides is actually correct. But a better way to do this, so here what I'm doing, if you think of this, imagine a circuit now that has reconvergence. Whenever there's reconvergence, I'm actually doubling it. It's as though I'm duplicating the parts of the circuit that had been replicated. It turns out I don't have to do this with conditional permutations if I start at the top. With one critical fact. Let me just conclude with this one critical fact. The critical fact is that it's on an ugly set of slides. So, okay, let me just conclude with this. For those who are inclined, it'd be great if you want to think or play with this. For this set of permutations here, A through E inverse, there's another very nice property that these permutations have, and that's the following. Let's say I've got A. So I've got a circuit that computes A. I don't want A. I want B. So this is going to be critical because in terms of the merging part, if I just try to do the merging and I don't duplicate the circuit, then sometimes I'm kind of stuck in a corner. I've got a circuit that computes A, but instead I want a circuit that computes some other permutation. It turns out you can transform any program, any conditional permutation program, that computes one permutation into a program that computes another permutation for free with a transformation without increasing the number of lines. Because for any permutation A, you can find some other permutation lambda where if you pre-multiply A by lambda and post-multiply A by lambda inverse, you get B. So for every permutation in this list A, you can find a lambda such that this construct gives you any other permutation you want. This lambda, then, you can simply tack it in every line. So every line of your conditional permutation. I'll really finish with this. So if we had a permutation X that was giving us A and identity, and then Y, B, identity, X, A, inverse, identity, Y, B. What we can do is we can just multiply each line by lambda, lambda inverse, lambda, lambda inverse, lambda, lambda inverse, lambda, lambda inverse, and so forth all the way through. So I just transform each permutation to some other permutation. The overall result will be now a circuit that instead of computing, suppose that it was computing C and we wanted D, we have a new conditional permutation program that computes D instead of C for free. This means that, in fact, we don't have to duplicate things when merging. All right. So I'll have to take that up again next time. But you guys will perhaps appreciate this topic when you begin playing around with it yourself. It's actually fun on the next homework to play around with these permutations. I do. I can email it to us. I think it was something like, because I saw it for the 4 problems, so I don't know what the average is. But for the 4 problems, it was around 80% of the average on each of them.
Okay. And then, are we going to get more quizzes?
Yes, the quizzes for some reason have fallen to the wayside, but it's on my to-do list to basically give you guys the full menu of quizzes. So,
Well, I'm worried like they're all going to get grouped up during like my finals.
no,
and
no, yeah,
final
yeah,
presentation and stuff.
yeah,
So-
they won't. I'll give them to you well in advance. That's the whole point of this course, that it should be relaxed in terms of the timeline.
I think John's.
Yeah.